Welcome back to another episode of NASA Space News. In 1967, Jocelyn Bell, a graduate student at the Mullard Radio Astronomy Observatory in Cambridge, UK, was studying observations from the Interplanetary Scintillation Array. Together with her advisor, Anthony Hewish, she discovered a source of repeating radio signals originating from the same location in the sky on a nightly basis. Bell and Hewish speculated that they had found a communication from an alien civilization due to the signal's regularity. It repeated every 1.33 seconds. They even dubbed the source LGM-1, which stands for Little Green Men. But as scientists discovered more of the same sources in different regions of the sky, they recognized the signals had to be natural, otherwise the aliens would be everywhere. Basically, a pulsar is a kind of neutron star, the ultra-dense leftover of a giant star's core. However, some pulsars spin more faster than others, with the fastest known spinning nearly 700 times per second. That's approximately 1 turn every millisecond, which is really fast. Astronomers also study a different kind of pulsar, called X-ray pulsars, which are objects that are accumulating mass. To provide just one example, if a pulsar has a partner star, the pulsar's absurdly strong gravity may rip material off the companion star and suck it in. It speeds up the substance to a velocity that's about equivalent to 2/3 the speed of light. This is a really incredible event to see, since the impact of this material on the neutron star's surface generates so much energy that the light released is in the X-ray region of the electromagnetic spectrum. The interaction of this material with a magnetic field, which may generate X-rays, can also lead to some really intricate physics. Recently, using the Neutron Star Interior Composition Explorer, or NICER, onboard the International Space Station, or ISS, an international team of astronomers has inspected the recent outburst of an accreting millisecond X-ray pulsar known as SAX J1808.4-358. Results of the study, published December 19th on the preprint server arXiv, shed more light on the nature of this source. The X-ray intensity of X-ray pulsars varies regularly, with periods as brief as a fraction of a second. When a low-mass companion star transfers its material to a slow-rotating neutron star via an accretion disk, the resulting object is called an accreting millisecond X-ray pulsar, or AMXP, which has an unusually short spin period. AMXPs are seen as astrophysical labs by astronomers and may prove to be essential in expanding our understanding of the mechanisms behind thermonuclear bursts. However, only a few hundred AMXPs have been discovered via the use of NICER and other space observatories. SAX J1808.43658, sometimes known as SAX J1808 for short, was first seen in 1996 by the X-ray satellite Bepo-SAX during an X-ray burst. Once X-ray pulsations were observed from this source, 2 years later, it was classified as the first accreting millisecond X-ray pulsar. The object has a neutron star and a brown dwarf orbiting it at a distance of around 11,400 light-years with a mass of about 0.05 solar masses. This system's orbital period was calculated to be around 2.01 hours. Since its discovery, SAX J1808 has had 10 outbursts, each lasting about a month, with a recurrence span of 2 to 3 years. The ISS's Monitor of All-Sky X-ray Image, or MAXI sensor, detected the beginning of a new outburst from this pulsar on August 19, 2022. Shortly after the outburst started, scientists headed by Giulia Iliano of the Rome Observatory in Italy began monitoring SAX J1808 in an effort to learn more about the pulsar's characteristics. SAX J1808 recently had an outburst, during which it faded from a high brightness of roughly an undecillion ERGs per second in about a week before entering a reflaring stage that lasted for about a month. Earlier explosions also exhibited similar characteristics. Previous analyses revealed that SAX J1808's spin frequency was decreasing at an average rate of 0.001 PHS per second, and the scientists' analysis of the recent outburst confirms this. An energy loss of 100 YG-cm3 is compatible with the rotation of a magnetic dipole of this size. evidence of orbital contraction since the previous epoch for SAX J1808 was detected for the first time in the past 20 years, according to the study's analysis of the orbital phase history. The long-term behavior of the orbit was found to be represented by a modulation of 11 seconds, with a period of 21 years by the scientists. SAX J1808 is predicted to have a fresh outburst in 2025. The paper's authors stress the need of observing the forthcoming outburst to verify the results of the Pulsar's orbital development. That's all for now. Make sure you don't miss any updates by subscribing to the channel. Also, if you enjoyed this video, consider checking out our previous videos. And for up-to-the-minute updates, visit our website at www.nasaspacenews.com. Thanks for watching.